For our second day, talking about trigonometry, identities, and equations, we're going to cover a couple of kind of basic, easier sets of identities, and then one that's a little bit more involved. So let's look back at our sheet of identities. Last time we've covered the ones that were highlighted. Today we're going to do these down here in blue. We're going to start with even and odd. So you can see down here, even odd identities. What happens if we take the 6 trig functions at the opposite of a certain angle? What happens to those? So back over here, we could just look at them, and I want to talk a little bit about why they are the way they are, but you can tell quickly some of them, if you take the opposite angle, you're going to get the exact same value anyway, like cosine. Cosine of negative angle is the same as cosine of positive angle. And sometimes, like with sine, you get the opposite if you change the angle to its opposite. So let's talk about what that means. Let's look at a graph of cosine. A graph of cosine starts at the top and it's symmetric about the y-axis like this, which means if you take the cosine of an angle, however many degrees you want, let's call this x degrees, and you take the cosine of negative x degrees, you're going to get the exact same value. You're going to get the same height because of this symmetry. And we've seen that in the unit circle. On the unit circle, the cosine of 30 and the cosine of negative 30 are the same because they have the same x coordinate. With sine, it has a different kind of symmetry. Sine looks like this. It starts at the bottom, goes up, down, and back up. So if we change an angle on sine to its opposite, if this is angle x, if we plug in negative x, we don't get the same height. But what we do get is the opposite of that height. If this is y, this is negative y. It has symmetry. It's just got rotational symmetry about the origin. So without further ado, what that results in are these. Our even functions are cosine and secant, because those have symmetry about the y-axis. Our odd functions have symmetry about the origin, and if you plug in the negative on those 4, you're going to get the opposite y value. Okay, remember, even odd. Even is like x squared. If I square 2, I get 4. If I square negative 2, I get 4. It doesn't matter whether I plug in the negative or the positive version. Odd is like x cubed. 2 cubed is 8, but negative 2 cubed is negative 8. It's kind of where they get their names, even and odd. Okay, so we can add this to our list of topics that have been discussed. Get rid of those. All right, so let's look at the section above. We're going to talk about, I know I've got just scribbles here under even odd, but the important thing is they're on your identity sheet. So on this yellow page, we're just kind of talking about why that is the case. So let's talk about cofunction. Cofunction is this blue section above the even odds. And what this is basically telling us is something you kind of already know from your unit circle talk. Complementary angles. If you recall from geometry, complementary angles add up to 90. And if you recall your unit circle, we've got some patterns in that unit circle. Let's just look at 30 and 60 right now. The sine of 30 is a half. But if you go up to 60, the sine and cosine have flip-flopped. Cosine 60 is a half. And that doesn't just happen for sine and cosine at 30 and 60. It happens at all complementary angles. So any two numbers that add up to 90. So sine of 10 equals cosine 80. Cosine 20 equals sine 70. And you could see that over and over again. Cosine of 70 is that number. Sine of 20, also that number. Okay, so this is something you probably could have come up with on your own, but it's on our sheet. And what's going to happen is if we ever need to get rid of, when you're trying to prove an identity, if your answer has a cosine in it and your starting point has sine of pi over 2 minus angle, and that could be 90, by the way, if it were in degree form, you can eliminate that sine term and then change it over to the cosine term. All right, so we're going to add those to the list of things. Those are the two kind of easier ones that you can already pretty much understand based on what you know on the unit circle. All right, next, this is the little bit more involved one. Sum and difference. We're going to look at expressions like this. Cosine of x plus y. What if we change the argument? The argument is the thing we're taking the cosine of to a sum. All right? What isn't true is this. I guess I should say, since the title is isn't true, I don't want a double negative, so this is not true. And this is what, year after year, time after time, students want to claim is true. It's kind of like, you know, it's exactly like this. Just because you have two things added together and that sum is squared doesn't mean that it's the sum of the two things squared. Just because we have two things added together and we're taking the cosine of that sum doesn't mean you just take the cosines individually and add them together. Same idea. This is an issue of order of operations. So what is true? What is cosine of x plus y equal to? Just in case you're not buying it, let's try cosine of 20 plus 30. Just to confirm. So this would be the cosine of 50. Cosine of 20 plus 30, the cosine of 50 is 0.64. Cosine 20 plus cosine 30 is not the same thing. All right, it's 1.8. So we have a problem. What is it equal to? Now, some of these identities, we're going to talk through the rationale, why they are the way they are. Some of them are a little bit more complicated. We could look it up in our textbook at any point. This is one of those where we're just going to know that it's here and understand that if we needed to prove it, we could, but for the sake of time, this one's not one we're going to talk through. So what is the cosine of x plus y? Well, here's the section, sum or difference of two angles. This one, you have to read it using this plus or minus. All right, so to save space, they've done a plus or minus in one. So the sine of a plus b, those are alpha and beta, there's just variables, could be a and b. The sine of a plus b is sine a cosine b plus cosine a sine b. So if the plus is on top here, then we use the plus here. If we needed sine a minus sine b, we would use the minus in both. And sometimes they flip-flop. So the cosine of a plus b is cosine a cosine b minus sine a sine b. And like I said, we're not going to talk in this particular video about why they are that. We're just going to know that they are that. So let's fix that example we just did a minute ago. If cosine of a plus b is cosine a cosine b minus sine a sine b, you catch up with myself here. Cosine of x plus y equals cosine x sine, excuse me, I'm going to double check that. It's cosine a cosine b. So cosine x cosine y minus sine x sine y. If that's the case, then we should be able to use that to figure out what the cosine of 50 is. Cosine of 50, which I'm thinking of as 30 plus 20. Just to confirm, obviously you would just type cosine 50 if you needed to know what the cosine of 30 plus 20 was, but with variables we're going to confirm using this example. So the cosine of 30 plus 20 should be the cosine of 30 times the cosine of 20 minus sine 30 times sine 20. And we should be able to get that answer, that cosine of 50, using this identity. All right, so the cosine of 30 times cosine 20 minus sine 30 sine 20. And there is that 0.6427, which you can see up on the screen. And just to double check again to confirm, cosine of 50, 0.6427. All right, so we've shown that that's what is true. So if you've got the cosine of a sum or a difference, sine or tangent to, you need to use these sum or difference formulas. If the plus and minus are combined, whatever's on top, use on top. So if you needed to do tangent of something, minus, you're going to use a minus there and a plus there. You'll get used to reading that. If you have any trouble with it, ask about it, but it won't take you long to get used to it. All right, so those are the identities we're covering in this one. Let's look at a couple of examples of the type of problems you might see. Cosecant 75. What I can ask you now is, without a calculator, tell me what the cosecant of 75 is. We only have a few select angles on the unit circle that we know values for. All right, 30, 45, 60, and angles like that. 75 is not one of those. However, cosecant 75 is made up of 30 and 45. Okay, so cosecant 30 plus 45, I think we can all agree that's the case. Since 30 and 45 are unit circle spots, and now I have a way to evaluate sum and difference, I can answer this with no calculator. You'll notice there's no cosecant, but we do have sine, and sine is the reciprocal. So what we're going to do is find the sine of 75 and flip it over. Right, so this is equal to 1 over sine 30 plus 45. So we have a sine of A plus B situation. Sine of A plus B is equal to sine A cosine B plus cosine A sine B. Sine 30 cosine 45 plus cosine 30 sine 45. All right, always just look back at your identities. I think I got that. Let me double check. Sine A plus B, sine A cosine B plus cosine A sine B. All right, I think I've got it. Now, again, we're doing this with no calculator because 30 and 45 are good spots for us. So this is 1 over sine 30. You're going to have to keep up to date with your unit circle. 30 degrees, sine's the y value, that's a half. Cosine 45, square root of 2 over 2. Cosine 30, square root of 3 over 2. Sine 45, square root of 2 over 2. All right, so far so good. We're using the sine sum formula, but we're putting it on the bottom because the actual question is cosecant 75 degrees. All right, so let's just simplify a little more. This is 1 over. A half times the square root of 2 over 2 is the square root of 2 over 4. And this is the square root of 6 over 4. If I add those terms on the bottom, I get the square root of 2 plus the square root of 6 over 4. And since it's on the bottom, I'm going to flip that over and make it 4 over the square root of 2 plus the square root of 6. And some of you just got cold chills because of those radicals in the denominator. You can leave it like that. If the directions specifically say you need to rationalize it and get those out of the bottom, you can. It would end up being the square root of 6 minus the square root of 2. But we'll just leave it for now. That's not the point at this time. All right, so how do we do the 75? We use 30, 45 in our new theorem. All right. Finally, we're going to prove an identity. We've started these. We've done some simple ones. They're going to start as we start learning more and more items on this chart, on this table of identities. You're going to be able to do more and more complex proofs. You are allowed to start on either side. Sometimes one will kind of lead you, I don't know necessarily to a dead end if you do correct steps, but sometimes there are simple and there are more complicated answers. If you look at this and you're like, I have no idea where to start, you just need to try something. If you try something and it doesn't work out, then try something else. And because I have the benefit of knowing the answer, this might not have been the first thing I tried, but here's what I'm going to do. I'm going to take this tangent and change it to sine over cosine. whatever you're taking the tangent of, you can change it to sine of that over cosine of that. That is a legal step. You might be thinking, if I see tangent of a plus b here, tangent of a sum, why not just use the tangent of the sum formula, right? Why not use this guy? Well, the issue with this guy is it creates a fraction with a bunch of other tangent terms in it. My answer, my right-hand side, does not have tangents in it. So somewhere I need to create some cosines, and that secant might be 1 over sine, and changing from tan to sine over cosine does that, all right? I don't know at this point if it's going to be the perfect, most elegant solution, but I'm just trying something. Another thing I notice is there's no pluses or minuses over here. I have one term. Over here on the left, I have two terms. So what I need to do is add those two terms together. So I'm going to consider this one to be cosine x plus pi over 4 over itself. So then I can add together the two terms. Okay, you could go from here to here. I just wanted to show you what I was doing with that one, just to make sure you got it. All right, so now what I see on top are two expressions that are sine of a sum and cosine of a sum. So the sine of x plus pi over 4, according to our newest identity, is going to be sine x times cosine pi over 4 plus cosine x times sine pi over 4. Okay, so that was all, that was this. All right, all I did was use my sine a plus b plus cosine of a plus b, cosine x plus pi over 4 is equal to cosine x times cosine pi over 4 minus sine x sine pi over 4. Okay, so that's here. And all of this still has the same denominator, cosine of x plus pi over 4. All right, so it's getting real big and complicated, but I can start to cancel some stuff out soon. Starting with what are the cosines and the sines of pi over 4. Cosine and sine of pi over 4 both square root of 2 over 2. So I'm going to take this cosine pi over 4 and change it to square root of 2 over 2 plus square root of 2 over 2 cosine x plus square root of 2 over 2 cosine x minus square root of 2 over 2 sine x, still same denominator. Might need to change that denominator in a minute, I'm not sure. Let me look back at my answer. Remember what you're looking for. Oh, I see in my answer secant of x plus pi over 4, and that's just 1 over cosine of x plus pi over 4. So I've already got that. This right here is going to serve as that secant. So if you're tempted to go, well, I just used a cosine x plus a plus b formula on that, remember, always keep your answer in mind. That secant is good. So we should be able to wrap this up. Negative square root of 2 over 2 sine plus square root of 2 over 2 sine. Those cancel. These two terms add. Square root of 2 over 2 cosine plus square root of 2 over 2 cosine is a square root of 2 cosine. I basically had two halves of that. And then, like I said, I've always looked back at my goal. Square root of 2 times cosine. 1 over cosine is the same as secant, so I'm going to take this, move it up. Square root of 2, cosine x, secant x plus pi over 4. So as you start to look for the smoothest path to here, realize your answer might look different than somebody else's. Sometimes there's a nice easy way, sometimes there's complicated ways, sometimes there's ways in the middle. Right? If you can start on the left and get to the right, you've got it. All right, and it doesn't need to be exactly the same path someone else took. All right, so for the sake of time, we're going to wrap this one up. We've got our even-odd cofunction and sum and difference. 3 new sections on our chart highlighted. We're going to move through this thing quickly. I'm having fun with it. I love identities. Young out.